Okay. Now you have to derive the moment of inertia of this rod about the given axis. Okay, as seen in the diagram, the rod of mass m length L is parallel to this axis and the distance between them is r. Do this, all of you. Okay, I got one answer as mr square. We'll see. Venle, how did you solve this?
Sir, every particle on the rod is r
Okay,
distance from the
fine,
axis
fine.
of rotation.
Good. See, this is a continuous mass distribution, the rod that is given. So moment of inertia of a continuous mass distribution, we'll have to write the moment of inertia of an element first, that is r square dm. And integrating that gives us the total moment of inertia. This is what we have been doing. Okay. So consider an element of the rod. Let its mass be dm. Its distance from the axis is the distance of the entire rod from the axis. Okay. So here, in this situation, from element to element, r will not be a variable. Okay, like you take a dm anywhere, the distance from the axis will be the same. So it becomes very easy to express the moment of inertia in this case. Integral r square dm. R is uniform. R is the same for all dm, so it can be kept outside the integral. And integral dm becomes the total mass. Therefore, the answer is mr square itself. Okay, because all the mass m is at the same distance r from the axis. Aishwarya, is this clear?
Yes, sir.
Okay. Next. Moment of inertia of a ring about its own axis. See, ring is basically a circle. Okay. We ignore the thickness. Can one of you tell me what kind of mass distribution a ring is?
Linear mass distribution.
Ring is a linear mass distribution, correct. So just for us to be able to visualize better, we show it as a thick ring, but let's ignore the thickness of the ring. Okay. Now, every circle has a center. If you imagine an axis passing through the center, perpendicular to the plane of the ring, okay, that axis, that line is called the own axis of the ring. Fine, it's somewhat like this. It should be perpendicular to the plane of the ring, passing through its center. This is what we call as the own axis of a ring. Same for a disk also. Fine. Assume the ring's mass is m and its radius is r. Usually for a ring, like the only dimension you need to specify is the radius. Okay. Fine. Derive its moment of inertia about this axis. Okay, when your answer is correct only, we'll just wait for 1 more minute. Aishwarya, your answer is also correct. Rishi, any answer?
I'm not.
Okay. Consider an element on the ring. Ring is a continuous mass distribution, no? So we'll have to find out how much moment of inertia one element contributes, and we'll integrate that to get the moment of inertia of the entire system. That's the general procedure. So you take an element of the ring somewhere here. Assume its mass is dm. Rishi, tell me, how much is its distance from the axis?
R, sir.
R, the radius itself. Okay, fine. Then how do you express the small moment of inertia that the element contributes? What is the moment of inertia of that element about this axis? It's a point element only, no? Mass is m, distance from the axis is r. So how much moment of inertia does it contribute about that axis?
Sir, is it I omega square, half I omega square?
Half I omega square is the formula for kinetic energy. Okay, anyway, see, I'm just asking you what is the moment of inertia of a point object which is at a distance r from the axis. That's the basic formula of moment of inertia, no, mr square. So here it becomes dm, mass of that element, multiplied with the square of the radius. Okay, you can visualize that in the other diagram also if you want. This element's mass is dm. It is at a distance r from the axis. So the moment of inertia it contributes is dm into r square, because mr square is the formula for moment of inertia of a point mass. Okay, so the total moment of inertia of this ring becomes integral of capital R square dm. Capital R is the distance of every particle of the ring from the axis. Okay, so you can put it outside the integral, and integral dm becomes total mass of the ring. Therefore, the moment of inertia of a ring about its own axis is simply mr square. Rishi, is this clear?
Yes.
You can use the same idea that we used for the previous problem. All the mass m here is at the same distance r from the axis. That way also we could have directly told that moment of inertia is mr square. Okay. Next, moment of inertia of a disk about its own axis. And we have to mention that it is a uniform disk. Uniform means the density is same all over. First, one of you tell me, what kind of a mass distribution is a disk? Linear, areal, or volumetric? What kind of mass distribution is a disk?
Areal mass distribution.
It's an areal mass distribution, correct. So assume the disk mass is m, radius is r. Just a moment. Derive its moment of inertia about its own axis. As I said, own axis is an axis passing through the center perpendicular to the plane of the disk. So it will be here. Now clearly, all particles of the disk are not at the same distance from this axis. Some particles are close, some particles are far. Maximum distance is capital R. Okay, let's do some qualitative analysis first before we get to the answer, derivation. For a ring about its own axis, we got it as m capital R square. Why? Because the entire mass m was at the same distance r from the axis of the ring. In a disk, what is happening? All the mass is not on that boundary. Some mass, very little mass is on that boundary. The other particles are closer than capital R to the axis. So you all tell me, do you expect the moment of inertia about this axis to be mr square itself, or less than mr square, or greater than mr square? And why?
Less than mr square, sir.
Okay, Vanilla, why do you expect it to be less than mr square?
So because most of the particles are nearer to the axis of
Good, good. See, r is the maximum distance of some particles, or R is the maximum distance of particles of this system from the axis, but there are other particles closer than R also. So had all the mass m been on the boundary, then it would have been mr square. But if particles come closer, moment of inertia decreases. Therefore, the answer has to be less than mr square. This kind of understanding is also important about moment of inertia of a system, generally for any system. Okay. So do this, all of you. Derive the moment of inertia of this disk about its own axis. This second diagram is when you look at it from an angle. Okay, axis passes through the center of the disk and is perpendicular to it. Okay, I can write a solid line. We expect the answer to be less than mr square. Okay. Can one of you tell me an idea? How will you proceed? It's a continuous mass distribution. Aishwarya, how do we derive moment of inertia of a continuous mass distribution?
So by integrating r square dm.
Okay. See, integral r square dm is the basic formula. That's fine. So if you can take an element of this disk, okay, call its mass as dm and the distance from axis as r, then you can do integral r square dm. But if you want to do that, you should be able to express dm in terms of dr. For a single element like this, it becomes difficult. Okay, because the mass distribution now is an areal mass distribution. And if you want to express dm in terms of dr, see, this distance can be called as dr. That's fine. But it's not a linear element. No, it's an element spread over an area. So we'll need this distance also to multiply those two and express the area of the element. Okay. So integral r square dm is the basic formula. It is difficult to use it in this case. So there are some other ways to proceed. Any other ideas, anyone? Okay. One thing you can do, the formula is I is equal to integral r square dm, right? If you take a single particle, dm is the mass of that particle and r is the distance of the particle from the axis. There is another way to look at this formula. You fix the distance r and then you can call dm as all the mass present at a distance r from the axis. Okay, you take an element, then take distance of element from the axis. That is one way to do. You take a distance first and see what all mass is present at that distance. Okay. In fact, if you remember, we had done something similar for center of mass also while deriving the center of mass of a semicircular disk and such things. We had to do integral y dm divided by integral dm, right? So what we did was we fixed a y coordinate and then we visualized all the mass at that y coordinate. Okay, you can do something similar in moment of inertia calculations also. So what we'll do is we'll fix a distance first and then visualize what all mass is present at that distance. We'll write an expression for it and try to integrate. Okay. So consider the disk along with the axis. Let's fix a certain distance from the axis first. Axis is passing through the center of the disk. It's perpendicular to your screen. Okay, the axis is perpendicular to your screen. Now, if you take a certain distance, let's say small r, okay, at that distance, you need to visualize what all mass is present. The mass present at that distance will be in the shape of a circle like this. You're fixing the distance from an axis, no? At a fixed distance from an axis in areal mass distribution, the mass present will be in the form of a circle itself. It will be like this. Okay, let's consider it as a thick circle. Just a moment. Somewhat like this. So this mass that I have indicated in gray is the mass present at the distance r from the axis. Now what we need to do is derive an expression for this mass, because now we are going to call this mass as dm. Clearly, that's not the whole mass of the disk. No, it's only a thin ring element of the disk. So indirectly, what we are doing is we are treating the disk as a collection of rings. Fine. So what we are going to do is write an expression for the moment of inertia contributed by this element. Now the element is in the shape of a ring, or you can look at it this way also. The entire mass dm of the element is at the same distance r from the axis. So can one of you quickly tell me how much is the moment of inertia of that gray colored mass about the given axis, which is shown in blue?
dm square.
Dm r square, it's in the shape of a ring. Okay, ring's moment of inertia about its own axis is mr square. This ring's mass is dm, radius is small r. So it becomes dm into r square. That's the moment of inertia contributed by this ring element. Rishi and Aishwarya, is this clear?
Yes, sir.
Okay. Now, to be able to integrate, okay, the total moment of inertia of the disk will be the integral of small moments of inertia contributed by the elements. That's the idea. Okay. So we'll need to do integral r square dm now. And to integrate this, you know what you have to do. You have to express dm in terms of dr. Okay. So again, we come back to those cases where we have to express mass of an element in terms of dimensions. And to whenever you are required to do such things, express the mass of some part of a system, you first look at what kind of distribution it is. We have already discussed that this is an areal mass distribution. Can one of you quickly tell me how do we express dm in an areal mass distribution?
So is it lambda dx?
Lambda is for linear.
So sigma dA.
Sigma dA, where sigma is the areal mass density or the surface mass density, total mass by total area. Okay, good. So we need to derive an expression for the area of that ring element. Do any of you remember the idea how to write area of the ring? Like I'll shade this area. We need an expression for this area. We had done this in case of a semicircular ring.
By r dr, sir.
2 pi r dr. Basically circumference of the ring multiplied with the width of the ring. Actually, you have to do outer circle's area minus the inner circle's area. But if you do it and approximate dr to be very small, then you will get the length 2 pi r multiplied with the width dr. So this length that I am drawing in yellow is the length of the ring element, right? That length will be 2 pi r, small r, and the width of the ring is dr. You multiply the length and the width, you will get the area dA. That's all. Therefore, dm becomes sigma into 2 pi r dr in this case. Good, we got dm in terms of dr. Now we can integrate and find out. Complete this, all of you. I want you to derive the total moment of inertia, which is integral r square into dm. dm is sigma 2 pi r dr. Substitute proper limits for r and get the final answer. Some of you may be knowing this already, but derive it properly. Okay, if you put the constants of the integration outside, sigma 2 pi are constant. Sigma is total mass by total area. Total area of the disk is pi r square. So that sigma multiplied with 2 pi is also constant. And you'll be left with integral r square into r, that is r cube dr. Integral r cube dr is r power 4 by 4. And we have to substitute the limits for small r. Rishi, can you tell the limits for small r to cover the entire disk?
Sir, is it 2 pi r?
What is small r?
The radius of the small.
Radius of the element. Okay. Now the whole system, the full disk, is a collection of such elements, right? So I'm asking you, from which value to which value should the radii of these elements vary to cover the entire disk?
0, sir.
0 is the starting value. Final?
R.
Capital R. So 0 to capital R. And when you substitute the limits in the integral, it becomes r power 4 by 4. Pi gets cancelled. R power 4 and r square. 1 r square will remain in the numerator. 2 and 4, 1, 2 will remain in the denominator. The answer you get will be m r square by 2. Is this clear to all of you? If you have any doubts, you can ask. Okay. For a uniform disk about its own axis, the moment of inertia is mr square by 2. Where m is the mass of the disk, r is the radius. Fine. Let us next consider a non-uniform disk. What do we mean by a non-uniform disk? It means the areal mass density, the mass per unit area, will be varying from point to point or distance to distance, something like that. So suppose there is a non-uniform disk. Assume its radius is 2 meters and its areal mass density depends on the distance from the axis. Okay, so from distance to distance, the density is changing. Let's say the areal mass density depends on the distance from the axis as r square. Okay. Fine. See, we take the disk as a collection of rings, no? Ring to ring, the radius will be changing. And radius to radius, the density is changing. Means different rings have different densities. Okay. So there are two things that you need to find out. First, okay, yeah, no need of that. Derive the moment of inertia directly about own axis of the disk. Radius of the disk is 2 meters. Areal mass density varies with distance as square of the distance. I'll just copy the diagram. Any answer? Okay, Aishwarya, how are you trying to solve this and where did you get stuck?
Sir, I got an answer is 64 pi by 3, but I'm not sure if.
Okay, tell me the steps.
Sir, I wrote dm is r square into dA.
Okay, dm is equal to sigma dA, which becomes r square dA. That's fine. And then
Sir, I wrote dA is 2 pi r dA.
dA is 2 pi r dr. Okay. Correct only. After that,
Sir, and then I use the formula to integrate it, sir.
okay, fine. Now see, the mass dm that we have taken is in the shape of a ring, and the ring's axis is same as the disk's axis. So I becomes integral moment of inertia of the ring element. That becomes integral. How do you write moment of inertia of a ring? Its mass multiplied with the square of its radius. So its radius square is r square, and its mass is this expression 2 pi r cube dr. Okay, dm was 2 pi r cube dr. Substitute that here. That's all. So 2 pi constant, put it outside the integral, and integral r square r cube is r power 5 dr. You integrate it, becomes r power 6 by 6. Substitute limits also. This is what you get. So pi r power 6 divided by 3. This is correct only. So basically why we took ring elements here is because the density varies from distance to distance from the axis. So at a given distance from the axis, the density is uniform. And at a given distance from the axis, the shape of mass you get is a ring. So we treat the disk as a collection of rings. Fine. Next. Uniform hollow sphere of mass m, radius r. Okay. One of you quickly tell me what kind of mass distribution is a hollow sphere?
Aerial mass.
Aerial mass distribution. Okay, we can consider this bubble as a hollow sphere. And whenever we derive moment of inertia, we have to specify the axis also. Suppose the bubble's mass is m, radius is capital R, and you have to derive its moment of inertia about an axis passing through the center of the bubble, center of the hollow sphere. Okay. Can any of you tell me the idea? What can be done? It's a continuous
So
mass
we can consider them as rings,
Correct.
collection of rings.
Correct. You can consider a hollow sphere as a collection of rings of varying radius. Okay, we did something similar in center of mass also when we derived center of mass of a hollow hemisphere. Just a moment. Yeah. A hollow hemisphere. Okay, we took half bubble there. You can take it as a collection of rings, and those rings we visualize that time. They look like onion rings. Okay. Yeah, somewhat like this. So the same kind of element we can take now also. So I'll just copy this. So this bubble that is there can be taken as a collection of elements like this, ring elements. Or if you visualize properly, the element kind of looks like this. Okay. And mass is there only on its surface. It's an areal mass distribution. This is the mass dm, and it's in the shape of a ring. And the given axis, which is a line passing through the center of the sphere, becomes the own axis of the ring also. Okay. But the radius of the ring is a variable from ring to ring. Let's call this radius as small r. So as you take different rings, the radius keeps changing. Okay. So instead of calling it x, we can call it as small r. Fine. So what we need is an expression for mass of this ring element in terms of that radius, which, as we have discussed in center of mass also, is difficult to express. Because, see, r is that horizontal distance from the axis to the ring. Then dr will be, I mean, mathematically dr means a small change in r. It should be in the same direction as r. Okay. But the slant length of that element that you take, which is dl that you see in the diagram, it's not the same as dr. Okay, you can see in the lower diagram also, I'm drawing it now. dl is that slant length. If you call this radius as r, then this horizontal length is dr. Clearly, they are not same. Okay, so it becomes difficult to express the surface area of that ring in terms of dr. Fine. Then if you want to solve this, how should you proceed? We find that it's difficult to express dm in terms of dr. So what do we do? In case of hollow spheres or semicircular ring also. Okay, that's why I said it is important to revise those derivations in center of mass. Anyway, if you consider the bubble as a collection of rings like this, and because it is becoming difficult to express dm in terms of dr, we convert both dm and r to some other variable, okay, which is nothing but theta. So see, this is the center of the sphere, no? Join the ends of this element to the center. They'll be subtending a small angle d theta. And imagine a horizontal line here. Call this angle as theta. Then the small angle subtended by the element is d theta. And the length of the element dl can be written as r d theta. Okay, where capital R is the radius of the bubble. And now the radius of this ring element, which is small r is from here to here. Can one of you tell me how small r can be expressed in terms of capital R and theta? We had done the same here also. We took help of theta. There we call that radius as x. What was x in terms of capital R and theta? Okay, someone unmuted, but I didn't get any answer. What was x in terms of capital R and theta?
R cos theta.
R cos theta, the horizontal component of capital R. Correct. So here, small r becomes capital R cos theta. Okay. And why did we get that slant length? Because we need an expression for the mass of this ring element dm. Now, you know, hollow sphere is an areal mass distribution. So dm is going to be sigma into dA. dA is that shaded area. How do we express that shaded area? We write it as circumference of that ring element multiplied with the slant length. Okay. dA is expressed as 2 pi r. That's the circumference of the ring element multiplied with the slant length dl. You should not take the horizontal distance dr. Okay. Therefore, dA becomes 2 pi. In place of small r, we'll write capital R cos theta. And in place of dl, we'll write capital R d theta. Therefore, the mass of the ring element dm becomes sigma into all this. 2 pi r square cos theta d theta. And the radius of the ring element is capital R cos theta. Okay, are these steps clear to both of you? Any doubt in this? Fine. Now we need to derive the total moment of inertia of this hollow sphere. That will be integral of moments of inertia of the ring elements. And what is the moment of inertia of a ring element? R square dm. We'll substitute that here. Therefore, I becomes integral. If you square the radius, it becomes r square cos square theta. And then dm is sigma 2 pi capital R square cos theta d theta. Okay. Now, capital R is a constant. Capital R is the total radius of the sphere. From ring element to ring element, what changes is theta now. Okay. As you go higher and higher, theta value increases. Okay. So theta is the variable. We'll have to keep cos theta terms inside and send the remaining terms outside. Sigma 2 pi r power 4 stays outside. And inside the integral, you will have cos cube theta d theta. Okay, we got somewhere, but this integration is slightly complicated now. Can one of you tell me how to integrate cos cube theta? Or integral cos square theta? We had discussed some ideas for that. Okay. Do any of you know the formula for cos 3 theta? That much trigonometry, I think you should have studied by now in 11th class. Cos 3 theta.
Four cos cube theta minus 3 cos theta.
4 cos cube theta minus 3 cos theta. Correct. So if you ever need to integrate cos cube theta, you can make use of this formula. From this formula, we can say that 4 cos cube theta is cos of 3 theta plus 3 cos theta. That means cos cube theta is 1/4 of cos of 3 theta plus 3 cos theta. So integrating cos cube theta is like integrating this, which is relatively easy to do. Okay, still we need to put some effort. So I, the total moment of inertia now becomes sigma 2 pi r power 4 is already there. And inside the integral, you will now have 1 by 4 cos 3 theta minus 3 cos theta d theta. 1 by 4 is a constant. We can put it outside the integral. And the remaining integral will split into two parts. Okay, let's just look at the integration part first. Those constants will include later. So this can be taken as integral cos 3 theta d theta minus integral. Okay, again 3 cos theta, 3 is constant. Cos theta d theta. Okay. What is integral cos 3 theta d theta? Anyone?
Sin 3 theta by 3.
Minus. Okay. Wait, not minus, sorry, plus. This is integration. No? Yeah. So it becomes 1 by 3 sine of 3 theta minus. This becomes integral cos theta is sine theta itself. Okay. And outside there were some constants, sigma 2 pi r power 4 divided by 4. And we still have to substitute limits. Okay, this is quite lengthy actually, but we have to do it. Fine. Now, let's go back to the diagram. Our aim is to find the moment of inertia of this whole sphere. Okay, to cover the full sphere, from what value to what value should theta vary? Or you visualize it like this. For the topmost ring, okay, topmost ring will be somewhat like this. Okay, a small ring at the top. You join its ends to the center. How much is this angle? Almost equal to
90 degrees.
90. For the bottommost ring, which is on the lower side, how much will the angle be for this ring? We are taking angle with the horizontal. How much will this be? Yeah, one of you said something.
Minus 90.
It has to be taken minus 90. Okay. So the limits for theta will be from minus pi by 2, or let's write minus 90 degrees to plus 90 degrees. Okay. Now we have to carefully substitute the limits. 2 and 4 I'll cancel. So it becomes sigma pi r power 4 divided by 2 into, first we'll substitute upper limit 1 by 3. Sine 3 into 90. Sine 270 is how much? Anyone? Sine 270. Sine 90 is 1. Sine 180 is 0. Sine 270 is minus 1. Okay. Minus of 3 times sine 90 is 1. Okay. That is when you substitute the upper limit. Now substitute the lower limit. 1 by 3 sine minus 270. Sine minus 270 is minus of sine 270. This becomes minus of minus 1, that is 1. Minus 3 times sine minus 90 is minus 1. Okay, we substituted upper limit and lower limit. So this becomes sigma. Sigma for the hollow sphere. What is the total surface area of a hollow sphere? Total surface area of a hollow sphere. Area of a sphere. Okay, 4 pi r square. So total mass divided by total surface area. That is the sigma for this system. Into pi r power 4 divided by 2. Into, let's simplify this. Minus 1 by 3. And there's a minus 1 by 3 becomes minus 2 by 3. There's a -3 and a -3 becomes -6, or I'll write it as -18/3. So totally this bracket becomes -20 by, why are we getting minus? Just a moment. Moment of inertia should come out positive. Why are we getting a negative sign? Cos cube theta is 1/4 cos 3 theta plus 3 cos theta. Okay, so there should be a plus here, and we should write the same plus everywhere. Plus fine. Now that bracket, there's a -1/3 plus 3. Again -1. -1/3 -1/3 is -2/3. Plus 3 is 6. That is 18/3. Is this correct? 3, 3, 6. Fine. 18 minus 2 becomes 16/3. Something is wrong. Something is still wrong. Let's check once again right from the beginning. So we took a ring element like this. Area will be circumference 2 pi r, and 2 pi small r is 2 pi capital R cos theta. Okay. Multiplied with the slant length. Slant length is r d theta. That's fine. So dm becomes sigma into dA. dA is 2 pi r square cos theta d theta. And small r is capital R cos theta. That's fine. So we'll have to integrate the moment of inertia of the ring elements. Integral r square dm. R square is capital R square cos square theta. Dm is that whole expression. We wrote it as it is. Then sigma 2 pi r square r power 4. Cos square and cos became cos cube. That's fine. And cos cube integral is cos 3 theta plus 3 cos theta whole divided by 4. I mean, cos cube is cos 3 theta plus 3 whole divided by 4. Outside we had sigma 2 pi r power 4. We kept it as it is, and that 1/4 we took out. Cos 3 theta plus 3 cos theta we had to integrate. Okay. Cos 3 theta integral is 1/3 sin 3 theta. That's fine. And 3 cos theta is 3 sin theta. That is also fine. To cover the entire sphere, angle should vary from -90 to +90. Everything seems to be right. Let's check the limit substitution again. Sin 3 into 90, sin 270 is -1. Okay. Plus 3 times sin 90 is 3 into 1. Okay. Minus 1/3 sin 3 into -90 this time. That is minus sin 270, which is minus or -1. That becomes 1/3. Okay. Plus 3 times sin -90. Sin -90 is -1. Okay. So -1/3 -1/3 is -2/3. 3 plus 3 is 6. I am writing it as 18/3. This way, if we proceed, what are we getting? Okay, this is fine only, no? Right. So Pi gets cancelled. R square r power 4, 1 r square will remain in the numerator. Okay. 2m r square by 3. So what have we derived? The moment of inertia of a hollow sphere of mass m radius r about an axis passing through its center. Okay. And we get it as 2 by 3 m r square. This is correct only. Okay. Yeah, Vanilla and Aishwarya, is the derivation clear?
Yes, sir.
Fine, fine. Okay, I just got confused with that 3. That's okay. Next, moment of inertia of a uniform solid sphere. Assume its mass is m, radius is r. Axis is again an axis passing through the center of the sphere itself. Okay. Can one of you tell me an idea? What will you treat a solid sphere as to derive its moment of inertia easily?
Sir, it's continuous disk.
You want to treat it as a collection of disks. Okay, let's see something we had already done. It can be done. You can treat a sphere as a collection of disks. Nothing wrong in that. But if you treat it as a collection of disks, okay, something like this, the mass of the disk element that you get, see, solid sphere is a volumetric mass distribution. You have to write dm is equal to like this, density into volume. The mass of the disk element you get will be pi r square dy, where r is a variable. Okay, like this expression, it changes to pi small r square dy, where dy is the thickness of the disk. And that is where we'll run into trouble. It will become difficult to express dy in terms of dr. It can be done, it's not impossible. Okay, like what we have done here. You can express dy in terms of dr if you want. Okay, but that will be very lengthy. Can you think of the solid sphere as a collection of anything else? Any other shaped elements whose moment of inertia we already know? Can you think of a solid sphere as a collection of any other elements whose moment of inertia we already know?
Sir, continuous hollow spheres.
We can treat it as a collection of hollow spheres. Correct. Just a moment. I'll take one diagram. Okay, let's say this is the solid sphere whose moment of inertia we are trying to derive. Its mass is m, radius is r. It's important to visualize the axis about which you are deriving the moment of inertia. Axis passes through the center of the sphere. Fine. Treating it as a collection of hollow spheres makes it much easier to solve. Fine. Let's consider a hollow sphere somewhat like this. See, we are looking at it from a side. So the sphere may look like a circle. Okay, consider it as a collection of thick hollow spheres like this. This hollow sphere, you can assume it has a radius small r and a thickness of dr. Now there will be mass in this thickness. That is the mass of this hollow sphere. You can call it as dm. So basically the idea is the total moment of inertia of the solid sphere is integral of the small moments of inertia contributed by the hollow spheres. Okay, so we need an expression for moment of inertia of the hollow sphere. And we just derived moment of inertia of a hollow sphere about an axis passing through its center is 2 by 3 mr square. Here it becomes 2 by 3 into dm multiplied with square of the radius of that particular hollow sphere. And to integrate this, we need to express dm in terms of dr. And what kind of mass distribution is a solid sphere? It's a volumetric mass distribution. So you have to write dm is equal to density, that is mass by volume, into the volume occupied by that thick shell element that we have taken, hollow spherical element that we have taken. Okay. Now total density we know. Total mass divided by total volume, that is 4 by 3 pi capital R cube. Can one of you tell me how to write the volume of that thick hollow sphere that we have considered? Volume of that thick shell. How can we express it? Okay, how did we write? Yeah, one of you unmuted, you can tell.
So the shell is hollow, so we can't write its volume.
No, it has some thickness. Because if you don't consider thickness dr, then how will you build a full sphere out of it? Okay, full solid sphere is a collection of thick hollow spheres. Okay, some thickness dr it has. It's so that's what I was going to ask. See, we considered a disk as a collection of rings. Now you may say, I mean, that time why did you not say that ring is just a wire? It won't have any width. Okay, you have to take rings which have small width. Fine. And how did we express that area? Circumference of the ring multiplied with the width. So same thing here. We consider the solid sphere as a collection of hollow spheres which have some thickness, small thickness, dr. And how do we write that volume? For a ring, what did we do? Circumference multiplied with the width. Then for a sphere, what we'll do? Area multiplied with thickness. That gives us the volume. Actually, what you should do is this outer sphere's area, not area, outer sphere's volume minus the inner sphere's volume you have to do. Okay. But the radius of outer sphere and the radius of inner sphere have only a small difference dr. So when you write volumes and subtract, you will see that the result is approximately equal to area into thickness. Okay. So dV can be written as area of that sphere, 4 pi small r square, thickness dr. So 4 pi small r square dr. This is how we get dm in terms of dr. Okay, 4 pi cancels. You get dm is equal to, send 3 to the numerator, 3m small r square dr divided by capital R cube. That is dm. Okay. Now don't blindly integrate r square dm because this entire dm is not at the same distance from the axis. The dm, the element that we have taken, is in the shape of a sphere, hollow sphere. Not every point of the hollow sphere is at the same distance from the axis, no? So you have to integrate the formula for moment of inertia of a hollow sphere. Therefore, the total moment of inertia now will be integral moment of inertia of the shell element or the hollow sphere element. And for hollow sphere element, the formula for moment of inertia is 2 by 3 into its mass. 3m r square dr by r cube into square of its radius, small r square. 3 cancels, 2m by r cube comes out of the integral. And you will be left with integral r power 4 by 3 by r cube. Okay, you'll be left with integral r power 4 dr. And integral r power 4 dr is r power 5 by 5. And if you want to cover the entire solid sphere, the radii of the hollow spheres should vary from 0 to capital R. Okay, this smallest shell having approximately 0 radius to the last shell having approximate radius of capital R. Fine. So limits will be from 0 to capital R. You do that, it will become capital R power 5 by 5. So 2m by r cube into r power 5 divided by 5. Answer becomes 2mr square by 5 or 2 by 5 mr square. So moment of inertia of a solid sphere about an axis passing through its center becomes 2 by 5 mr square. For hollow sphere, it is 2 by 3 mr square. Solid sphere, it is 2 by 5 mr square. Had you treated it as a collection of disks, you would have gotten the same answer, but procedure would have been lengthy because expressing the volume of a disk in terms of dr will require some extra steps. It's much easier this way. In center of mass also, it was easier to take the sphere like this as a collection of hollow spheres. Okay, so let's quickly revise what all formulas we derived today. First one was just an application of basic formula for moment of inertia. Next, moment of inertia of a ring about its own axis. What do we mean by own axis? A line passing through the center of the ring perpendicular to it. That's called the own axis of the ring. Okay, and we see that it is mr square because all the mass of the ring is at the same distance, capital R. Simple formula. Next, disk about its own axis. Remember what we did. We treated the disk as a collection of rings. And we got the answer as mr square by 2. Non-uniform disk was like a problem. You don't have to remember the answer. Next, uniform hollow sphere. We treated it as a collection of rings. We made use of angle theta in the derivation and we got it as 2 by 3 mr square. And uniform solid sphere, we treat it as a collection of thick shells. Okay. And we got the answer as 2 by 5 mr square. Okay. Now, some more cases are there. Like we have to derive the moment of inertia of a hollow cylinder, solid cylinder. That's all. These are the basic shapes whose moments of inertia you need to remember. Now, we also know that when the axis changes, the formula for moment of inertia can change. Okay. So how to deal with, I mean, for a given system, you can take an axis of rotation anywhere, no? And for every axis of rotation, you can have a different formula for moment of inertia. So you can't remember infinite formulas for each system, no? So there should be some other way to derive moment of inertia about some other axis, not these standard ones that we have considered. Okay, so for that, we have two theorems. So moment of inertia of hollow cylinder, solid cylinder, and those two theorems, which will help us find out moment of inertia about other axes. Those things we'll discuss in tomorrow's class. Okay, thank you all. We'll continue tomorrow.